Hello everyone, my name is Arronde Pérez. I am from Cuba and I'm currently a PhD student at the Institute of Smart System Technology at University of Klagenfurt. This time I would like to present you the results of our research that are described in the paper titled Automatic Uncertainty Propagation based on the Unscented Transform. With respect to metrology, the quality of measurement results have been expressed in terms of uncertainty, which quantifies the doubt about how well the result of a measurement represents the value of the quantity being measured. In order to provide an international consensus on evaluating and expressing uncertainties, the Guide to the Expression of Uncertainty in Measurements and its subsequent supplements were developed. They suggest the use of Taylor series approximation and Monte Carlo methods to perform the uncertainty calculation. The problem is that when we are in presence of an advanced measurement process, to perform the uncertainty propagation can become a tedious and complex task. And in order to address these kind of problems, many software solutions for automatic uncertainty propagation have been developed, which are basically based on the previously mentioned method. Having such tools for uncertainty propagation is extremely beneficial, especially when dealing with measurement models that involve complicated equations, since it reduces the effort for computation of uncertainty because this is done automatically, and it allows consideration of uncertainty in early design phases and can be easily applied for a wide range of applications. However, linearization and Monte Carlo methods present some limitations, which is why in this work we propose the use of the unscented transform for automatic uncertainty propagations. As far as we know, there is no software tool for uncertainty calculations based on the unscented transform principle, and that's why the existing method and the suggested unscented transform are realized in an uncertainty toolbox for MATLAB environment in order to provide a more complete software solution. Well, the measurement model is in general nonlinear and should include all quantities that significantly contribute to the measurement result uncertainty. Between the methods for automatic uncertainty propagation, we find the linearization and Monte Carlo approaches, as we mentioned before. And linearization is based on the Gunn approach and treat all uncertainty contributions identically, considering Gaussian distributions and linear propagation toward the measurement results. On the other hand, Monte Carlo is suggested when linearization of the model provides an inadequate representation, and it has been widespread used for approximating arbitrary probability density functions, where a high number of samples is required. This method presents some drawbacks. Linearization, for example, gives an inaccurate result when nonlinearities cannot be neglected, and Monte Carlo presents a high computational cost due to the dimension of the sample space. And that's why we introduce a method based on the unscented transform principle. This approach was originally presented to improve the performance provided by the standard Kalman filter in nonlinear state estimation problems. And the key idea is that it should be easier to approximate a probability distribution than to approximate an arbitrary nonlinear function. And it have been employed for predicting mean and covariance in nonlinear system through the evaluation of a small number of sigma points which are deterministically chosen. The procedure that we use here is the scale Unscented transform, and this can be summarized in 3 steps. The first one consists in the determination of the sigma points. In the case that we are dealing with an n-dimensional problem, we just need to determine 2n plus 1 sigma points using the scaling parameters where alpha and kappa are influencing how far the sigma points are away from the mean. The second step is the propagations of the sigma points through the nonlinear transformations in order to obtain a cloud of the transformed points. And the third step lies on the estimation of mean and covariance matrix from the weighted average and weighted product of the transformed points. Where here we want to show you some details about the implementation of the unscented transform principle for the automatic uncertainty propagation. The unscented transform was implemented based on the object-oriented programming capabilities of MATLAB that supports operator overloading and considering that every complex mathematical expression can be executed as a sequence of basic arithmetic operations or elementary functions. The user should define the inputs at uncertain variables, and this is all it have to do. This is all the work for the user. The rest it's done automatically by the toolbox. And then the inputs quantities and the associated sigma points are individually defined, keeping track of the correlations with respect to primary uncorrelated variables, which is done by the Carhoonen-Love decomposition. Then each measurement equation is split in terms of its elementary operations and functions, and the sigma points are propagated sequentially. The dependency list is updated at each intermediate step, and finally the estimated value and standard uncertainty of the output is displayed. This can be done because the scaled unscented transforms allows any set of sigma points to be scaled but an arbitrary scaling factor in such a way that the first two moments are preserved, which means that the scale unscented transforms overcome the dimensional scaling effects. The advantages of these methods is that reduce the computational burden in an evaluation of the combined uncertainty of the output quantities in a general nonlinear measurement system. Well, an uncertainty toolbox for MATLAB was developed by our research groups, and this one comprised the three methods, linearization, Monte Carlo, and unscented transform. And here we defined a data type for each of these approaches. As far as we know, this is the first software solution for automatic uncertainty propagation based on the unscented transform principle. And we find it extremely beneficial because this allows the analysis of correlations and dependencies between variables, and it also supports complex quantities, matrix operations, and more advanced functions like FFT or interpolations. And this tool provides quick access to perform and analyze faster contributions and mutual influences that we will see in the examples applications. The first application example consists in a simple coordinates transformation from Cartesian to polar plane. Here we illustrate how to perform the calculations with the toolbox, assuming that we know the mean and the standard uncertainty of the Cartesian coordinates. We declare it as uncertain variables, and then we just need to apply the transformation equations to get the estimation and standard uncertainty of the radial and angular coordinates. The calculations were performed using the three methods provided by the toolbox, and to have a better idea about the precision of each approach, we execute the Monte Carlo methods with 1,000 and 1,000,000 samples. Here in the polar coordinates, we can see the linearization completely fails, and that UT may give us the same result as Monte Carlos with 1,000,000 points, but in this case, UT only needs to evaluate 5 sigma points. The second example presents the forward kinematic model of an hydraulic forestry crane, which is being under investigation as part of a project intended for automation of log manipulations. The figure shows the geometric model of the crane, and we aim to investigate the movement of the end effector by means of moving the hydraulic cylinders. A nonlinear relation maps the cylinder length into the end effector displacement done by means of the homogeneous transformation matrices. The cylinder lengths are subject to some noise given for the measurement noise of displacement sensors or the process noise of the dynamical model of the cylinders, which is why they are declared as input uncertain variables, and this is all we have to do. Just declare our inputs as uncertain variables, and then we can have access to some useful information just for free. This figure shows the end effector path from position A to B. The solid red lines depict a simplified model of the crane, which is plotted to have a better perception of the operational space. And here we can see that for each point in the workspace, we have the information about the elliptical region of uncertainty, and we can also trace back the source of uncertainty without do any additional computations. It is shown in the top right. We have the information about which parameters influence more to the output uncertainty, and we can get a feeling of what should be improved. It is also possible to get the covariance and correlation matrices between any set of parameters that we can be interested in. To summarize, we demonstrate that the unscented transform can be utilized for automatic uncertainty propagation, and that in many situations it offers advantages such as higher accuracy and lower computational efforts compared to the common methods. The presented approach and utilization of unscented transforms, linearization, and Monte Carlo in a common toolbox is very flexible, provides an intuitive way of switching between the propagation methods, does not require a lot of training. We believe this is crucial for a wide utilization of automatic uncertainty propagation and consideration of uncertainty throughout the entire development process, from the early concept and design phase all the way to the final production phase of certain devices. Thank you very much for your attention, or as we say in Spanish, muchas gracias por su atención.